Hi, we're continuing with cell biology and life science in a nutshell. We're learning about molecules found in the membranes of cells, such as in phospholipid molecules, which are contained in the membranes of cells. And we were learning about ether and ester bonds, especially how significant they are in affecting the membranes, the phospholipid bilayer membranes. So, again, ethers are carbon, oxygen, carbon linkages, while esters have two oxygen, COO groups. And so, the effect of the ether linkage as compared to the ester linkage on the structure and properties of lipid bilayers is of interest on studying how the membrane or the bilayer, phospholipid bilayer, is affected by these various linkages. Um, so, there have been studies comparing DPPC, which has two 16 carbon saturated chains attached to the glycerol backbone via ester linkages, with DHPC, which has ether linkages on both chains. One dramatic difference is that DPPC forms a conventional gel phase at room temperature, while DHPC, which has the ether linkages, hydrates. It is converted to a normal. It is converted to a chain interdigitated phase. To demonstrate this, this diagram shows the difference. So the interdigitated phase seems to be more linear, shown here, while the gel is more at an angle, like a diagonal. So these are the ether linkages. So straighter ester linkages more on an or angle. One of the motivations of studying ether versus ester linkages is to test theories that propose that the hedge group interfacial region is the determinant of water permeability through membranes. Changing the head group, so including the phosphatidylcholine and glycerol backbone, as well as the ester versus ether linkages in the head group, while the chains starting from the second carbon, etc. So these various orientations of the bonds help orient lipids based on the glycerol backbone and the ether linkages or various linkages. The water permeability is changed. The thickness of the head groups, aka the steric area of the hydrocarbon regions, and the bonds affects permeability data. The areas of the lipids, and also electron density models are taken of the various groups, such as methyl groups, etc. Also, permeability ratios are taken, and X-ray structural studies are done also. Sliding occurs also of the head groups on opposite sides of the bilayer. This occurs through towards the center of the bilayer, so that the terminal methyl groups and other groups can overlap with the glycerol groups. Double bonds, as a note, and dipolar bonds, carbon to hydrogen, have higher electron densities than single bonds. So in the studies, we have here distance from bilayer center. So 0 is the distance, and the further the distance, and these are showing a gel phase polymorphism of ether-linked dihexadecyl phosphatidylcholine bilayers, and the structural determinant of water permeability through the lipid membrane. So the more closer you are to the center of the bilayer, the less the permeability. And on the sides, the higher the permeability, or on the sides being at the further away from the center, which is more non-polar, full of more lipid, and on the sides there's more polar, and you have more of the head groups, etc. So more permeability on the sides away from the center of the bilayer. Water permeability and polarity on the two sides of the bilayer. Phospholipids are therefore an amphipathic molecule making up the bilayer of the plasma membrane and keeping the membrane fluid. Phospholipids consist of a glycerol molecule, two fatty acids, and a phosphate group modified by an alcohol. So they have hydrophilic polar heads and hydrophobic nonpolar tails. The phosphate group is a negatively charged polar head, which is hydrophilic or loves water. The fatty acid chains are uncharged nonpolar tails, which are hydrophobic or dislike water. Phospholipids consist of a glycerol molecule, two fatty acids, phosphate group, modified by alcohol. The phosphate group is negatively charged. And the fatty acid chains are uncharged. So differences in the length and saturation of the fatty acid tails are important because they influence the ability of the phospholipid molecules to pack. So the glycerol is right here. Then you have the phosphate group. Then the fatty acid tails. If you have a saturated fatty acid, it's all single bonds, and the tail is not kinked, so it's straight. Unsaturated fatty acids contain a carbon-carbon double bond, therefore the fatty acid tail gets a kink in it. So that's the hydrophobic tail, hydrophilic head. In the bilayer, you have two of these facing each other, making the nonpolar core with two facing fatty acid chains. And on the exterior of the cell membrane, on the cytosolic side, or the inside of the cell, you have more polarity. Excuse me. It would be either on the exterior of the cell membrane or the cytosolic side of the cell membrane. You're going to have polarity. So on either side of the cell membrane, you can have soluble water soluble polar groups, again shown here. So it's like a symmetrical arrangement with the two phospholipid molecules facing each other, making permeability on either side of the membrane, on the exterior of the cell and the interior of the cell. And summary, phospholipids consist of a glycerol molecule, two fatty acids, and a phosphate group modified by an alcohol. The phosphate group is negative, hydrophilic. Fatty acids are uncharged and hydrophobic. The tails are hydrophobic, facing inside, away from water, meeting in the inner region of the membrane. The heads are hydrophilic, face outward, towards the exterior of the cell or towards the cytosol, attracted to intracellular and extracellular fluids and various molecules used for signaling, etc.